Right. Hi, I'm a second year PhD coming into my third year, so still very much learning. But yeah, as I wanted to briefly introduce what I'm going to talk about, I'm going to talk about my project background because I'm again partnered between NPL and UKEA. So I'm an IK student. I spend some time. I work technically at NPL. I also do some collaboration with UKEA. I then want to briefly introduce the 50IC technique, and I want to discuss what I've been working towards, which is actually using yttrium oxide to actually enhance the DIC capabilities because we've been struggling with the speckle pattern. And then I'm going to talk about what I've kind of been doing on the current joints that I've been looking at. And then I briefly want to discuss methodology of the nano-indentation, how we do that for residual stress and also just generally, and how we do depth profiling and how it can be used in many other ways. I won't oversell nuclear fusion because I think we've already done that. It gets a bit boring, but it's very useful. It can be, hopefully, it could be an exhaustible energy source. If we can prove it, it can be amazing for humanity in general. One of the things I always loved is that Jet's plasma is actually 10 times hotter than the center of the sun when it was operating. So that was 150 million Celsius. Just gives you some sort of understanding. But yeah, so obviously looking at the DT reaction, but during that reaction, it creates actually a really harsh environment for materials. So there's many things that we need to look at. So that's part of my project, is to eventually lead on to understanding these things. Well, that got squished a bit. Yeah, so what I'm looking at is actually within the vacuum vessel. I'm studying mostly between two joints at the moment. So I'm actually trying to study how the effect of brazing can affect the residual stress state and see how detrimental that is going to be. Is it going to cause a preliminary failure? Is it actually that bad? And what other, I need to understand the microstructure and things like this. So at the moment I'm looking between two different joints. One just has a brazed, just the brazing foil in the center, which you can kind of clearly see is kind of sunk in almost to the urethra. But I've also got a copper interlayer in there as well, which actually has been usually formed to kind of help reduce residual stress. But also I think it may help with another thing, which I'll discuss in a bit. But fusion itself from materials is quite a hard environment. So one of the key challenges that they have for the materials itself, obviously, is the high temperatures. It's also the fact that you've got really high radiation doses, and maybe they get annealed out, but there also could be actually long-lived issues from that. And obviously high heat fluxes, which in Omar's presentation, you may see some work on that. Again, I think we've kind of understand residual stress, 3 types, all that. Tried to save some time. But most important, what I want to talk about is what residual stress and the structural integrity, how that actually impacts from the joints that I'm looking at. So obviously in brazing, because you've got 2 different joints, the main cause of residual stress is actually the fact that you've got CTE. So you heat it up, they join together, fine, there's no stress. As it cools down, that is then locked in. And you need to understand that. But obviously there's other things at play, which I will discuss, is like my joint as well. Like tungsten has iron has an affinity to actually go into tungsten, something called Kirkendall diffusion, if you're aware of that. It quite happens quite regularly. I want to quickly go on to discuss what 50IC is. And one of the problems that I've been facing is the speckle pattern generation. I've been looking at using, I'll discuss that actually. So 50IC itself is a method of basically incrementally milling and removing material. And as you remove the material, you can then take an image, and then using that image, you can then basically put a load of windows on that you want monitor. And each window can be then calculated for the strain field. We can do that in both X and Y directions. And technically, if you have that, you can kind of then work out any direction. So that's pretty much it. So one of the things I've been looking at is understanding the speckle pattern generation. So one of the things I've been looking at is yttrium oxide, because yttrium is quite a sputter resistant material to xenon ions. Because we tried many other things, like you can do obviously GIS systems and things like that, but like obviously GIS is quite a good system, but it takes a long time. You can be spending hours to do each experiment, and I need to do lots of these, to be honest. So I would be spending a lot of time, wasting a lot of expensive time, equipment time. So trying to reduce that is an intent of using yttrium oxide. And then it's relatively adjustable. So you can choose different particle sizes. You can kind of optimize it for the experimental parameters, like what different view sizes, what different ring cores or whatever you would like to do. And yeah, so what I found is it roughly seems to be quite a good way. So there's something called bias error, and bias error is a way of actually commonly to test if your speckle pattern is good. And it's usually used for like SEM, DIC, because what happens is the speckle pattern, you actually, over an increment of about a single pixel, you basically do sub displacements up, and I did this in about 40, 50 steps. And basically monitoring that, you can use the fact that DIC and also interpolation and the image is all done through like a quadratic or cubic interpolation. And as long as you match the interpolation methods, you can actually see you get this beautiful sine wave. And basically the sine wave is a fundamental of a few things, but one of the key fact parameters is the speckle pattern. So depending on if you've got a good speckle pattern, you would have a low bias error, which is quite important. So one of the things we wanted to start off with is actually understanding how does the amount of the nanoparticles affect. So if you've got a really high amount, then obviously you might be not necessarily looking at your surface anymore. You start to question what your DIC is actually analyzing. Is it just the particles moving about or things like that? But in the sort of bias error from the beginning, so I changed the spraying times just very briefly as a sort of early experiment to sort of understand. And you can see that really that the bias error seems to be relatively the same. So it seems to be relatively resilient, but obviously there's still for me the question of like, how resilient is it? Is it actually going to be just, am I actually testing the nanoparticles or am I actually understanding my sample? But in preliminary experiments, if I summed the actual, just the SEM stubs and compared it to previous work that we've done, just looking at an etched surface, and it already shows that the bias error is lower. So that seems to be a good thing. And then I kind of wanted to move on to the microstructure, what I've been doing very preliminary on my joints, because I've only just recently received a new batch. But during the actual brazing, I find that martensite forms quite readily in the urethra 97. So obviously my sample is very hard on the urethra side, which is quite clearly seen here, but you can see a drop in hardness because of the copper interlayer. And yeah, I basically started all of this really quite recently. And yeah, this is my EBSD map. You can see that the grain structure on the iron side is very fine, but you've got the roll texture of the tungsten. So as I mentioned, that iron has an affinity to diffuse into tungsten, and that's one of the things I want to quantify because there's these two problems. Yes, residual stress is important, but the structural integrity could be reliant on the fact that I've got a really brittle interlayer. So from literature, I found that the formation of these can be a very hard interlayer, intermetallic compounds. And that could be really important to understand because although I may have really low residual stress or really high residual stress, I don't know yet, I may find that the failure point isn't related to residual stress, it's completely related to the intermetallic compounds. So what I've been looking at really is I've done some EDS just generally to understand. You can see that there's this affinity where the brazing falls into my sample, into the iron side of my sample. My iron goes directly through. Because obviously at the beginning of brazing, the foil was in the center of those two joints. And this is where I found that the intermetallics are forming, which is about a micron in size. It's relatively small, but I think I would like to do some like fib DIC or nano indentation along this sort of section to actually understand what is going on there as well. And then I'm going back to methodology again. So to just briefly discuss how we're doing, obviously nano indentation, I don't know how familiar people are with that, but in generally, we're kind of adapting it to use it for residual stress. And two of the ways we're doing that is using Lee's model. And with Lee's model, you can do biaxial residual stress measurements if you can actually find a way to separate your X and Y, which is how we use that with 50IC. We can separate that quite a bit, and also EBSD. And through depth profile, with the fact that we can use a continuous stiffness measurement in nano indentation, it allows you to do depth profiling of nano indentation quite readily. You compare. So yeah, with the residual stress measurement, as Tan mentioned, we have our ring core as our stress-free reference. So using that, we can directly compare and then do a line scan directly and regionally pair the pillars to the line scan and then understand the residual stress from nano indentation. I've also briefly mentioned how to just generally get mechanical properties from nano indentation, but I think if anyone's familiar with nano indentation, they should already know these things. So this is sort of preliminary work regarding the depth profiling, and we want to understand it better. But we kind of originally kind of came up with this idea of like these three major bands. Like nano indentation is in itself is quite prone to noise, especially in the first like few hundred nanometers. And it's quite important to make sure you actually understand that and obviously mitigate that. You don't want to take your residual stress value from this region because it's obviously not worthwhile. But we need to actually kind of come up with a way of like algorithmically understanding how we divide up these regions and how we quantify these regions. At the moment, it's me doing this by eye just as an idea, but we need to think about how we can work that. But we could also think about how hardness as in general could be quite interesting because it may be that as we go through the sample, that the hardness is quite variable, as you can see, but we want to understand how maybe that could also be intimately relate together. And then obviously, because we're using nano indentation, we can do other things as well, which is like fast mapping. And with fast mapping, you can achieve an array like that in probably about 15 minutes. So it's quite impressive. But there's a few issues that we need to make sure we're comparing, because one of the major problems with indentation at that sort of speed is you've got really high strain rates. And then obviously, if I'm doing Lee's model, which is directly comparing the loads, I've got really high strain rate and a really low strain rate because my nano indentation, my stress-free reference is without at just like sort of standard strain rates. And then I got a really high strain rate map. I need to then think about how to sort of make these correlate to each other because strain rate sensitivity is a major thing. But the idea is that we can kind of look and understand the regional effects. For example, as you can see, the brazed dendrites that form into the iron from previous, we'll kind of see how it kind of correlates in these maps as well. In conclusion, I find that the urethane 97 obviously has formed the untempered martensite, which obviously induces the residual stress across that, but that's not directly related to CTE. So I need to think about how that actually correlates together. And obviously I'm more focused on the understanding of CTE because it's quite easy just to temper out martensite if needed. And really, yeah, I think I need to understand the intermetallic compounds and think about how I can compare them and see the difference between the two, especially in terms of residual stress, because I think it could be quite important. Right, future work, this is where most of my work is to become. I need to understand the microstructural evaluation between the two different joints, really, because I've only compared it onto the braze samples. And yeah, I need to work on the nano indentation to kind of build that further up and hopefully create a big story where I can understand this a bit better. Right. And lastly, I just want to thank the EPSRC for my funding, my IK studentship, and obviously thank you for your attention.